So we're going to take a look at the so-called Fermat point of a triangle. So as you can read from here, there is a story behind it. Fermat was a famous French mathematician. He is probably most well known for the so-called Fermat's last theorem, but that's not the point of this particular discussion. Here, he thought of a point inside a triangle called point P, later known as the Fermat point, such that if you draw a line connecting this point to each of the three sides, the three corners of the triangle, we call these lengths as A, B, and C, as you can see from this diagram, then he asks, is there such a way to find a point such that the length A plus B plus C would be as small as possible? Okay, that point is called the Fermat point. So he wrote a letter to the to the Italian mathematician and physicist Torricelli, who was famous for the so-called Torricelli device to measure the air pressure. That's again another story. He proposed that challenge to Torricelli. Torricelli was able to rise to the challenge and solve the problem. He found that point P, the Fermat point, is where these three triangles that you see in this diagram, alpha, beta, and gamma, each equals 120 degrees. Okay, that's how we find point P. Now, it's not easy to prove this mathematically from pure trigonometry point of view. And if you're interested, there are plenty of ways, plenty of resources online you can check how that's proven with geometry. But this is a physics course, so I'm here to talk about how we solve this problem using an unconventional yet still very convincing way. That is from a physicist's point of view. Okay, we solve a math problem from a physicist's point of view. Usually it's the other way around, but we have it here. So before we can tackle this problem, we have to look at some general principle when it comes to potential energy. Okay, potential energy. Now we know that if you consider a bowl like this, right, and if I drop a marble into it, right. So let me draw a marble here, and this marble will roll down the this bowl, and it's going to keep on going. Okay, it's going to keep on going. It may go up and down a little bit, but eventually, where does it go? It's going to settle here, right, at the bottom. Right? Or more simply, if you consider a case of free fall, everything falls from a certain elevation down until it reaches the ground. It will never stop. It just keeps on going until it reaches the ground. Okay, and if you consider a rope, okay, if I draw a rope that's flexible, okay, I draw a rope like this, and I suspend this rope between two fixed points A and B at the same level, let's say. Can you find the shape of this rope if it's fully flexible? Well, the shape is determined by the locations of points A and B, the length of the rope, and also gravity. Gravity pulls the rope down, right? It turns out the shape of the rope is such that when it assumes the final shape, the overall potential energy of the rope is minimum. And that is, we consider this rope here at various points, right? Various points. And let's say each point I divide it into equal amount of mass, okay? And then if you then add this distance, okay? This distance, and then this distance, and then distance, you measure everything from the line AB. You find when all these distances add up to maximum, that's how we get the shape of this rope. Okay, and that is that's when the potential energy, the overall potential energy of all these guys are as small as possible, as low as possible, because after all, it's equal to the potential energy measured from line AB is negative mgy, right? This is y for each particle of mass m, right? So when the sum of all these y's is minimum, you will get the shape of this rope. And so from these three examples and countless others, basically you get the same idea. The idea is that if you have a particle which is inside a gravitational field and is influenced by gravity, then the particle is going to move. And where does it want to end up? It wants to end up where the potential energy is the lowest. That is why it ends up at the bottom of this bowl. That's why it keeps on going until it meets the, it meets a table or the street or whatever. It cannot stop going until it can no longer go any further, because it's want to go further and further down to minimize the potential energy. Okay, so potential energy is minimized. That's where you're going to stop. Okay, so when you see something is already stopped, that means the potential energy has been minimized. So keep that in mind. Okay, it's not just for gravitational potential energy. If anytime an object is driven by a bunch of forces, each is a conservative force, so there's a potential energy associated with it, then the object will reach equilibrium only when the potential energy, the overall potential energy, becomes minimum. Okay, but in this case, we just have to consider one such force, which is gravity. So it's going to go as low as possible before it stops. Now, given this idea, let's go back to the Fermat problem. This is the mass version of the Fermat problem, but we are going to construct a setup, an actual setup using our consideration of physics, especially gravitational potential energy. So here is the construction. Let's see how we can do that. Okay. We are going to build something like this. We take a cardboard, okay? We take a cardboard and cut it into triangle. So imagine you have a cardboard, right? And it's being cut into a triangle like this. So here's the triangle in question. Okay, and we're going to put this cardboard on a flat supporting platform, which is this green cylinder. Okay, so the top of the cylinder is horizontal, it's flat. So we rest this triangle cardboard on top of this cylinder, so it's balanced. Now, here's what we're going to do. We are going to drill 3 holes at the 3 ends, the 3 corners of this cardboard, all right? And then I'm going to take out 3 strings, okay? I'm going to take out 3 strings and tie them together, 3 strings and tie them together at one end here, somewhere here, okay? And string number 1, I'm going to take string number 1, and I'm going to take that string and let it go through that hole at point A. Okay, let me do a better job drawing it. Okay, so I'm connected. So the string goes like this. It goes through the point, goes through the hole at point A, and it's going to go through the hole and it's going to hang down, and I'm going to add a little mass here, M, at the end. So it supports a mass M here at the end. Okay, and then I'm going to take take the second string, right? I'm going to take the second string and let it go through point B, the hole at point B, and it goes down and supports another weight of the same exact mass M, right? And finally, I'm going to take the third part of the string here and let it go through this hole at point C. And I'm going to support another mass M. Now, there's 3 strings may not have the same length. Okay, they don't have to have the same length. But it turns out that, assuming there's no friction, okay, there's no friction. This connecting point here, it's going to move around a little bit until it settles. The whole thing settles into an equilibrium when nothing moves anymore. My question is, what happens when it settles down, when nothing's moving? Okay, when nothing's moving, it turns out that since nothing's moving, this point, whatever that point is called, the 3 forces must add up to 0, right? I mean, that's from the balance of force, right? The 3 forces, I'm going to use a different color to draw the forces out. Okay, so there's a force, F1, F2, and F3. Now, all these 3 forces must add up to 0. So here is force 1, here is force 2, and here is force 3. They must add up to 0 because that point P is massless. We cannot have a net force on something with 0 mass. Okay, so F1 plus F2 plus F3 must be 0. But what is the magnitude of F1? Isn't this mg, right? Isn't it just mg? Same can be said about the magnitudes of F2 and F3. They all have the same mass. When you have 3 forces of identical magnitude, and they all go through the same point, and they add up to 0, that only happens when these 3 angles are equal to each other. What I mean is these 3 angles alpha, beta, and gamma by symmetry, right? You got 3 vectors of equal magnitude, right? And they add up to 0. So clearly, alpha, beta, gamma must be all equal to each other, but they add together to 360, right? So alpha plus beta plus gamma equals 360, and they're all equal, and therefore each must be equal to 120 degrees. So alpha plus beta plus gamma equals 360, and alpha equals beta equals gamma, because the 3 forces must add up to 0. So that means alpha and beta and gamma must all equal to 120 degrees. Okay, now is that point P here the Fermat point? This point here, this point P here, is that the Fermat point? If it is, then we proved our result. Of course, there's a key step that's still missing, and that is, can you show that when these 3 angles are all equal to 120 degrees, can you show that A plus B plus C is small as possible within the triangle? That is the key point that identifies the Fermat point, right? So how do we show that? Well, remember we talked about potential energy. Okay, we talked about potential energy. You know, everything goes down to a point where the potential energy is as low as possible. Okay, now we have an equilibrium here, obviously established because nothing is moving, right? And that means the overall potential energy of the 3 mass system must be as low as possible, which means the 3 masses must, as collectively, reach a position as low as possible. Now the strings, each string has a fixed length, right? Has a fixed length. If you want them to go as low as possible, that would mean that this length plus this length plus this length are as low as possible, as long as possible, because that's how far they are below that plane of the triangle, right? So that's our reference point for gravitational potential energy. You want x, y, and z, the sum of x and y and z as great as possible, so you can lower the potential energy, right? But remember, again, the length of each string is fixed, even though they don't have to be the same. If x plus y plus z is as long as possible, that means a plus b plus c must be as small as possible, don't you think? Okay, so that means point P is the Fermat point by definition. So you see, from our consideration of minimum potential energy for equilibrium, we have shown that the Fermat point is where these 3 angles, alpha, beta, and gamma, are equal to 120 degrees each. That's a simple and elegant proof of the Fermat point location using physics.